we were solving user equilibrium. We had 2,500 vehicles per hour coming from the highway and 1,000 vehicles per hour coming from the on-ramp. That adds up to 3,500 vehicles per hour. Because the vehicles are not going to be flying away, jumping from here to here, and not changing their mind and going back, one of the formulas that you have is 3,500 equal to Q1 plus Q2. Okay? That's a formula that people usually tend to forget. So that's one of the formulas. The other formula depends on the user equilibrium condition. The user equilibrium condition entails that the vehicles are going to split themselves onto these two routes in a way which is going to be provides identical travel times. So what we're going to have is T1 equal to T2. So the T1, which is the time taken on the upper route, is going to be the same as T2, which is the time on the lower route. When you equate these two, we notice that C1 is given. However, C2 is not provided. However, instead of C2, we have an additional formula, which is the green shield relationship representing that link. When we remember the formula of Vs equal Vf minus Vf over rho j rho, and we notice that it has the same form as U equal 100 minus 0.65 K, we realize that 100 is actually Vf. So on this curve, 100 is the free flow speed. So that's the speed when volume is 0 and when density is 0 and there are no vehicles on the road. Okay? So that is Vf. Now, minus 0.625 K, we know that K is the density. K, another name for it is rho. So we know that 0.625 then means the ratio Vf over rho j. Because we know what Vf is, which is 100, we can calculate rho j. After getting both of those variables, we put them in the formula of Qmax equal rho j times Vf over 4. Qmax is the maximum flow that I can get through that link. So through this link, how many vehicles I can go through, the maximum flow. The maximum flow has the meaning of the capacity. From this curve, we were talking about volume or flow, and it's limited by capacity. Okay, so based on the density volume curve, so we calculate C2 in that way, and basically C2 equal Vf times rho j over 4, and it ends up being 4,000 vehicles per hour. We equate T1 equal to T2, and we end up getting Q1 equal 2206 and Q2 equal 1294 vehicles per hour. In order to check your work, what you can do, because this is solving two equations, two unknowns, is putting them in the formulas of T1 and T2. So if T1 equals 6.65 minutes, what is T2? 6.65. Okay, so because of the user equilibrium condition, they will end up being the same. If it's not, then you've done a calculation mistake. Okay, now you're supposed to do the same for system optimal. Okay, first of all, do you have any questions about the solution? Please ask me.
I didn't even get to see it. Okay.
Here.
Okay, let me.
Do you have any questions about the solution of the user equilibrium? This is how, this is the selfish way of doing traffic assignment. This is how what you see in general in real life because of how people act while driving. But this is not what the system wants. Okay? This is not what traffic operators want. What traffic operators want is system optimal. So it's minimizing total travel time. Now, so it's asking here, first of all, it says 20% of the vehicles in the network are equipped with in-vehicle navigation units capable of displaying personalized routing information provided by a nearby TMC or a traffic management center. If the TMC wishes to use the equipped vehicles to optimize the network performance, what percentage of the equipped travelers should be sent rerouting information, and which route should be recommended? So before you figure that answer out, you need to figure out what is the system optimal assignment and then based on that, figure out what percentage of the vehicles to send information to. Okay? So if you're solving this in terms of system optimal rather than user equilibrium, how would you what would Q1 and Q2 be? To remind you of the system optimal analysis, you have to have equal marginal times, and marginal times are defined as the derivative of the travel time with respect to Q. Okay? If you don't know how to solve derivatives, I'll come and help you. So it's the derivative of travel time in terms of Q. Okay? So you have the travel time equations. You have to find the marginal.
We should just do the derivatives on the board and give that to them.
Let's see. Maybe they know how to do them.
I'm sure James knows how to do it, but
Grade 9s have taken derivatives? Yeah? No? Okay, we'll help you.
Why is m equal d times m?
Where are you? Here?
Yeah, is that 3 t's or an m?
TTT, travel time, total travel time.
Oh.
This means the derivative. Okay, let's start. M1 and M2. M1 is the derivative of T1, and M2 is the derivative of T2. Yeah, TTT is like T1 or T2, so it applies for both. It's total travel time. Okay, so after getting the user equilibrium solution, now we're solving for system optimal. So this is what the traffic operator would want. This would be the best performance or utilization of the system. So for system optimal, we find M1 and M2. M1 is the marginal travel time of the upper link, and you calculate that by as the derivative of Q1 times T1, and M2 is the derivative of Q2 times T2. So this is basically the derivative of the total travel time on each of those links. And based on the system optimality conditions, you can equate M1 and M2 to each other. And we have the same formula of Q1 plus Q2 equals 3,500 because you want to satisfy that demand. And you end up with M1 equal M2 equals 7.8. So you end up with these Qs, and then when you put them in, you find out that M1 and M2 equals 7.8. What about T1 and T2? Are they equal? No. They're not, because there's actually a minute difference between them. So T1 is 5.94 and T2 equals 6.94. So some vehicles would need to go through a longer route so that the total travel time for the system as a whole is minimized. Yeah?
Where did you get Q1 and Q2 from?
So we have M1 equal M2, which gives us one equation relating Q1 and Q2.
Yeah.
The other formula is Q1 plus Q2 equals 3,500. So you solve it as two equations to unknowns. So you can do Q1 equals 3,500 minus Q2, and then put that in the other within here. And you have two equations with Q2, and you solve for Q2. And then you put Q2 inside the equations of M1 and M2, and you get the same thing. This is just for a check. And then, again, you put them in equations of T1 and T2 in order to get the values. So you have, with user equilibrium, ending the travel times being, let me just show you. So the travel times being 6.65 minutes. And with system optimal, one route is going to be faster than that. One route is going to be smaller. But this is what you need to do in order to have to minimize total travel time. The question that, so basically you can think of it in this way. So user equilibrium 2206 and 1294, system optimal 1618, 1882. Quite a bit of a difference between them, right? So the problem was also asking if you can only contact 20% of the vehicles, if you can communicate with only 20% of the vehicles, they are the vehicles that have the new, I don't know, German cars or something. So they have the technology through which you can contact them, or like built-in navigation systems. How many of them would you contact, asking them to go to which route? Okay? So the assumption here is that if you don't contact them, they'll be going through user equilibrium. If you contact them, you can ask them to change their route. So you can only contact 20%. So first of all, you have to assume that the remaining 80% that you can't contact will be arranging themselves with the user equilibrium conditions. And the other 20%, you have to see how you can change so that you end up in total with this. Okay? So this is the diversion that's needed in total. So 2206 minus 1618, you want 588 people to go from route 1 to route 2 in order to end up with 1618 here. However, only 700 vehicles are equipped. Okay? Now, we cannot say that 500, out of the 700, we contact 588 people to tell them to go to route 2 because it's a ratio, right? Because out of that 700, already there's a ratio that will be taking system optimal. So it has to be a number far higher than that. So basically, this is taking into account where the original 80% were going and doing the difference. You'll be getting the number of vehicles that need to be shifted from route, that need to be receiving this information is 933. Okay? Now, however, we can only contact 700. That's why what we'll do is we'll tell all of the 700 to go from route 1 to route 2. So it will not be sufficient, but it will be far closer to system optimal than user equilibrium. Okay? So this is another, I guess, limitation of the technology. If you don't have enough market penetration meaning the number of vehicles that you can communicate to, you can't achieve some of the optimality that you're seeking. As you can see in this case, the number of vehicles that we actually wanted to contact. So this is actually 80% out of 3,500. We wanted them to give us 588 in total changing. That's why we end up with 933. So it's going to take us very much close, very close to system optimal, but not fully. Okay, so when would user equilibrium and system optimal be giving you the same results? When do you think this might happen? When there are no cars. So when there's no congestion, they're going to be very similar. When you have lots of congestion, what do you think is going to happen? Are they going to be similar? Are they going to be different? They're going to be very, very different. Okay? So when you have a growing congestion, the results between these is going to be diverging. So you're going to have very different assignments between these two conditions. Now, in programming computers to solve these problems, this is how you represent them. It looks a bit difficult, but it's actually not. It's just systematic. And then this is an optimization problem. So for user equilibrium, you're trying to equate the two travel times. That's why you on the curve, that's the area under the curve. This is calculus again, guys. And for I'm going to skip these. This is just a representation with to solve this problem. Let's see. System optimal formulation. Okay. Now let me just show you an important concept in transportation. So you have Q equals 6. This is the number of vehicles that I want to send, and I have routes 1, 2, 3, 4. I have these 4 links. Okay. And T1 of x1 is 50 plus x1. T2 of x2 is 50 plus x2. So they're similar. And this is 10x3 and this is 10x4. Now, when I solve this, actually, when I look at this, I'm going from this point to here. How should I divide this this queue? I have 6 vehicles.
So 3 goes
Half. Why?
because
It's symmetric. So queue link 1 looks like link 2, and link 3 looks like link 4. So x1 equals 3 basically, x2 equals 3, and then all of them will have 3 cars on them. That ends up giving us this is travel time. So 83 time units for both sides. And the total travel time, which is calculated, as we said, as the queue times the travel time, gives us 498. Okay? So 83 times 6 will give us 498. Now, we come to this and we add a link. We add a link in the middle. We say, this is taking so much time, why don't we add an additional highway here? Okay? And we want to see the performance of user equilibrium and system optimal. So what happens here, what happens with system optimal is it doesn't use that. It's actually the link is here. It doesn't use that. It keeps on using the other ones. However, with user equilibrium, because now we have an additional route, what user equilibrium does is it makes the travel times of all of those routes equal, right? So if a person is here, they'll be like, oh, this road is empty. Why don't I take that one? So some people switch, and you end up with basically 1/3 of the vehicles, so 2 in this case, 2 on that route and 2 on the other routes. Okay? Now, this makes sense, right? If there's another shorter route, why don't I take that? When you calculate it, you end up with the travel times of these 3 being 83, 83, and this middle route, which is not being used, which has this performance function, this highway, being 70
what's 7?
minutes. But no one is using it. Okay, so they're using these 2, and the total travel time is 498. For user equilibrium, because you equated these 3, because people were selfish and they were changing routes, they kept on changing routes, and what the equilibrium that they arrived to, all of the routes are going to have identical travel times, right? Okay, identical travel times of 92. And total travel time is 552. So although they were thinking that they were going to end up with shorter travel times, all of them suffered together, and all of them now have longer travel times, just because they decided to shift to that. So all the people in system optimal here are better. Actually, the first 2, because the third one is not being used. However, everyone here is suffering, and they're suffering together because of their selfish behavior. Yeah?
But wouldn't the middle one take shorter time because it's closer?
If you put one vehicle, yes, right? But then as vehicles keep on changing their routes, you can do the math. You have 2 vehicles here, okay?
Yeah.
In order to take that route, you still need to go down and go up and then go down. This is the highway that you have. The highway is here. The highway is not through here. Link 5 is going from this point to this point.
Yeah.
So in order to use it, you're still going to go down, go up, and then go down. Okay? Someone decided to put the highway there. So you go down, you go up, and you go down. So if you do the math, these 3 routes have the same travel time, right? However, they're all bad. This is called Braess's paradox. Okay, so the Braess found this, and this just shows that in some cases where everyone is taking the shortest route or trying to take the shortest route, and through that path they're ending up with user equilibrium, this equilibrium is actually really bad and really bad for all of them. This happened with a newly built highway in Singapore. After they realized this is what's happening, guess what they did?
They destroyed it.
They shut it off. A highway that is not being used. Volume on it is 0. Because if they start using it, because of the demand around the area, what's ending up happening is everyone's suffering together. So this doesn't happen every day. It needs specific demand to match the specific capacity, but it is possible. And it just shows that user equilibrium is not always the best, especially not always the best for even particular people. And it might end up that everyone will be suffering together.
So why would anyone take the middle road? Because
Well, let me tell you why. Because if you're here, if you're taking 83 minutes, if you go to the middle road, it will take you 70.
no, doesn't make sense though, because you're obviously going longer than.
I'm showing you. If you take the middle one, okay, 30, 10, 30, it will take you 70. So you go and take it. But if more people go and do that action, together, you're suffering together. Remember, transportation is not something that we said it depends on human behavior. Okay? It depends on human behavior. So it's you get the performance based on the aggregate. Your performance is not only dependent on you. When you join a highway, the amount of time that it will take you depends on how many people have joined earlier, are already there, are going to join later, are going to leave the highway. So that's why there's a social responsibility of understanding that. That's why, for example, Castra works on ramp metering, which shows that if you reduce the inflow from the ramp, everyone is going to gain. Some people on the ramp are going to suffer a bit, but when they eventually join, they're going to have a reliable travel time. Okay? So it takes a bit of change in people's mentality to understand that in order to be able to do the policy changes and implement those technologies in order to solve the transportation problem. Remember, our point is we don't want to be on the right-hand side, which is the congested side. We always want to be on the left-hand side of the density volume function, or the volume density function. Okay? And this is just an example to prove that it might happen. And you need to be careful with, of course, where you're building the highway, especially if it's not needed. Yeah?
Is it due to congestion that it takes longer?
It is.
Doesn't have to do with it.
Well, it is due to congestion because of the vehicles that are coming in. But there's another aspect, especially with the math here, is that this third route shares these links with the other routes. And if you decide to go on that route, you're also bothering people on those routes. Okay? And that's the place where the travel time is very big. It's 40 and 40, and you're using that, you're going through that multiple times. That's what's shooting up the travel time. So it could be, for example, that the 401 is not going to be used a lot, or you're only using a section of the 401. However, if multiple routes are using that critical part, then that's going to add up the delay for every single vehicle that's going through it. Okay? Okay, so we explained most of these. So adding the new highway actually made the network worse. So under user equilibrium, people are trying to minimize their own travel time, but in this case, it ends up to backfire. And